Welcome back to the workshop. We're continuing on in section 9.1 today on sequences, and we want to take a look at the squeeze theorem for sequences. So if we have two sequences, AN and BN, that both converge to L, and if we have that CN, some third sequence, is between those two, eventually, then we can conclude that the limit as n goes to infinity of Cn is also equal to L. Because if Cn is between An and Bn, then it must converge to the values between what those converge to. But they converge to the same thing. So this must converge to that as well. Again, this just needs to be true eventually. So if it isn't true for the first 2 or 3 terms, or even the first 100 terms, that's not a big deal. As long as we can eventually get somewhere that it's true for everything that follows. So if we hit the millionth term and it's true for everything after the millionth term, then we're fine. It's true eventually. All right, so let's determine if the sequence converges, and if so, find the limit. Well, spoiler alert, it converges. How do I know? Well, because otherwise I'd have another example. But for this sequence with the given a sub n, we want to determine if this one converges, and if so, find the limit. Well, convergence is defined by if the limit exists. So, of course, we want to find the limit first to determine the convergence. So, the limit as a sub n, or as n goes to infinity is what we want to evaluate. But, of course, I don't want to start right off with the limit. What I want to do here is I want to use the squeeze theorem and observe and recall that the sign of anything, n, x, theta, whatever variable you're using in there, of course you're going to end up with values that are between -1 and 1. Well, what good does that do me? Well, it does me a lot of good because that's not my entire sequence, right? If it were just this, then that wouldn't do me any good at all, right? That's just an oscillating sequence that does not converge. But my sequence, my terms in my sequence, have a denominator of 3n plus 1. So if I take -1 divided by 3n plus 1, this is less than or equal to the sine of n divided by 3n plus 1, which is less than or equal to +1 divided by 3n plus 1. Now, we have to be very careful about what we're doing here. First of all, notice that the denominator is never 0 because we're looking at natural numbers, natural values for n. 1, 2, 3, 4. So positive times a positive is positive. Add another 1, it's still going to be positive. So we never divide by 0. But also, we're never dividing by a negative number. So the inequalities stay, everything stays, since 3n plus 1 is strictly greater than 0. Okay? That's a very important note to make. All right, next we can simply apply the limit to each of these terms in the inequality, the sequence of inequalities here. So the limit as n goes to infinity of -1 over 3n plus 1 is less than or equal to the limit as n goes to infinity of the sine of n divided by 3n plus 1, which is less than or equal to the limit as n goes to infinity of 1 over 3n plus 1. Of course, the limit on the left and the limit on the right are easy to calculate. Both of those will go to 0, right? A constant divided by a number that gets larger and larger and larger and larger. Right? This is going to go to 0. So 0 is less than or equal to the limit as n goes to infinity of sine of n divided by 3n plus 1, which is less than or equal to 0. So, of course, that limit is equal to 0. Hence, the limit as n goes to infinity of the sine of n divided by 3n plus 1 is equal to exactly 0. Excellent. So that's an example of the squeeze theorem. We got a little bit more to look at in section 9.1, so I'll see you guys back here in the workshop in just a few.